Hello, my name is Zachary Chenoweth, and this is my presentation of Lab 3, Task 3, Particle Filters. So for this task, we have to use particle filters in order to have our robot navigate the maze and visit every cell in the maze without knowing its location um, within the maze. Now, the lab description did say that we will always start in cell 16 facing north, but we were supposed to pretend like the robot doesn't know which cell that it started in. However, we can always assume that we're facing north. So starting with the code, we have our general initializations of the IMU and all of our sensors. We have our initial pose array list. This is just for when we initialize the particles. So that way we initialize them to the cell that they're in and the orientation and such. This grid here is to let the robot know what the map looks like. So this designates all the walls and stuff like that. Because in order for the particle filter to work, we need some sort of data structure so that so the robot knows where all the whatnot. Because if it doesn't have this, it won't work. Each of these lists represent the cell, and all these numbers are represent these. If it's a 1, that means there's a wall. If it's a 0, there's no wall. And then the first number is if the cell is visited or not. This function here will just print the visited cells as we go along, and this was provided to us in the lab files. This orientation just keeps track of the current angle that we're facing. Since I'm going to be turning based on time when we do our turns, I'm just going to approximate and change this angle by 90 degrees each time. Here we have a class called particle, which we use for initializing each particle, and each particle is going to have a position similar to like this up here, and a weight, which is the probability that the particle is in, like the robot is in that cell. This function initializes all of our particles and uniformly distributes them to each cell. We are required to have at least 80 particles, so I have our particle count to 80, which is going to distribute 5 particles per cell in the beginning. And this, again, is just because we have to uniformly distribute them. Here we have our measurement model. Because this is a non-noise solution, our noise is going to be 0. I have a list that holds all of our probabilities. And we're going to start out by getting the distance sensor readings. So we're going to read the distance sensors and check if there's a wall. If there is a wall, we're going to set the S values to 1. Otherwise, we're going to set them to 0. And then we're going to check those compared to the expected values to get the probabilities. So depending on the direction we're facing, we'll change what walls we're expecting in each cell because of the orientation. So we have north, south, east, and west respectively. And if you go in here, we're going to check if each of the sensors are equal to each other. If they are equal, meaning that the expected is like, let's say, for example, the expected is a wall there. There is a wall there, and we're reading a wall. Then our probability that the particle is in that cell is going to be 1 minus the noise. Otherwise, it's just going to be the noise. So in this case, because it's a non-noise solution, it's either 1 or 0. We do that for each particle, and then we're going to multiply all the particles, or all the probabilities together to get a overall probability. And we're going to append that to that list. And then we have to normalize those probabilities because they need to be normalized in order for this to work. So we get the total by summing up all the probabilities, dividing by each probability by that total to normalize it. And then we're going to go ahead and update all the weights of the particles in each cell. And then we're going to return that distribution. Our next function is our importance factor. This is going to be used for the resampling step to determine how many particles should be in each cell based off of probabilities. So for the importance factor, we're basically going to multiply the weight of the particle by the number of particles in that cell. So initially, each cell is going to be 5. And for example, let's pretend that the probability that the robot is in cell 1 is 1. So, and initially there are 5 particles in the cell, so we would multiply 1 by 5 to get 5 as the factor, and that's the importance factor that we're going to use. And we also are going to have to normalize it. So we got to do the same thing as we did before, get the total, divide each factor by the total to normalize it, and that's going to be all our factors that we're going to use for the resampling step. In the resampling step, we're going to actually determine the number of particles in each cell. So we multiply each factor that we calculated before by 80, and we round that number to the nearest whole number to get the number of particles we believe should be in that cell. Now, because we do it this way, the probability will make the total number of particles that we want to put in more than the actual number of particles we have. So we want to make sure that we keep the same number of particles at all times because we are never losing any particles. We always have 80 throughout the whole process. So I fixed any issues with that by doing this. We take the total number of particles in this new distribution for the resampling. If it's not 80, so if there's some difference, then we're going to find the difference by taking 80 and subtracting that total, and then finding the max value in the distribution. So the in the factor list. So the cell that we want that has the highest particle count, we're going to subtract the difference from there to even it out. The reason I take it from the highest one is because it's less likely to be affected than if I were to take the lowest from the lowest value. Then after that, we're going to go ahead and redistribute all the particles based on the numbers we calculated before. And then we're going to return our particle distribution. Here we have our actual motion functions. So forward moves the robot forward. We use the position sensors to move it about 10 inches each time. Left turn uses kinematics formulas to calculate how much the velocity we would need to turn 90 degrees in 1 second. Left or right. So these functions are the same, just direction is different. So we want to turn 90 degrees in 1 second, so we use kinematics to calculate that. This function is what actually calls those above functions to move the robot, as well as keeps track of what motion we just performed in order to do the motion update later. So here we have if the previous motion was a left or right turn, we want to prioritize forward motion first. Otherwise, we want to prioritize a left turn, then a forward motion, then a right turn in that order, with left turn being the highest priority and right turn being the lowest priority. The reason we did that is because we need some algorithmic way to navigate the maze to make sure we hit all the cells no matter what the map looks like. Change orientation basically will just update the orientation or the angle based on the turn. Again, because we're turning based on time, these are going to be approximated to 90-degree differences. So we update based on that. Here we have our motion update again because the noise is 0, and this is the non-noise solution, so the noise is going to be 0. If the motion was a left or right turn, we're just going to update the orientation of all the particles because we want to make sure the particles are facing the same way as the robot, just for ease. Normally in a particle distribution, you will have some, if you have noise to the IMU when you're turning, you're going to make sure to account for that noise by making some of the particles change orientation and some of them not. If we have a forward motion, we're going to update those. So we're going to go ahead and get the current particle count in each cell, and then we're going to update based on the walls in each cell. So depending on the direction we're facing, if there's an expected wall in the direction we're facing in that cell, we're not going to move the particles. Otherwise, we're going to go ahead and adjust where the particles are by calculating the number of particles we want to move, subtracting them from the current cell we're in, and then adding those particles to the new place we're moving. And that's the same for all these. And then we're going to update the distribution for this new motion and return the distribution. Check visit is going to print all of our information, our estimated position, our particle distribution, and our visited cells. If the number of particles in a few cells is the same, so if we have multiple cells that are the highest amount, we're going to print the number of possible cells that we can be in, because we don't know its exact location, because they're all equally likely to have the robot in it. Otherwise, it's going to actually print out the position, so the XY coordinate, as well as the cell number and the orientation. Particle distribution, so we can see the particles moving throughout the as the robot's moving, and then the cell to see the visited cells. Check done is just going to go ahead and check and see if we have visited all the cells in order to stop the robot. Here's our while loop, so we're going to go and do this these steps while we haven't visited all the cells. So it's going to keep performing these steps until we've explored all the cells. And that's to print our information, do the measurement model, resample, move, change our orientation, and then motion update. And it's going to keep doing that. So that's the code. Let's go ahead and see it run. As you can see, it prioritized the left turn first, and we can go ahead and see how the particles are moving. So you can see the particles moving along, and then after a certain amount of motions, all the particles will converge in one place, and then now we know where our robot is. So it's going to print the estimated position, as well as update our grid as it's moving forward. You will notice that these two cells here say they haven't been visited despite us having started in this cell and moving to this one. The reason is because previously, when those cells were going, the particles had a high count in two places that were exactly the same. So we couldn't precisely say that the robot is in this cell or this cell. So we just assume we haven't visited them yet and let the robot explore and revisit those cells, despite the fact we have already been in those cells. So as you can see, the robot's making its final motions as it's moving to the end. We can still see the particles moving with the robot. And then once it sees that, after it finishes its motion, it's going to see that it's visited all the cells. So it's going to go ahead and stop the program successfully. And then that's the end of that program. So this was the non-noise solution. Let's go ahead and look at the noise solution. Here we go. This code is basically exactly the same with some minor changes, being that we're now accounting for noise. So now these formulas here that we're using to calculate probabilities will account for that noise in the distance sensors and the position sensors in our motion. Again, all these functions are exactly the same as the previous one. No real changes there. And then the motion update, again, we're accounting for noise. Those are the only two places that we're really changing, because now we have to account for the noise in the sensors. Let's go ahead and see this one run. And again, you can see it's basically going the same direction as the previous one, but you can see that the distribution of particles is a bit different because now we're accounting for noise. So after several motions, you can see that it's starting to, all the particles are starting to heavily go into one place, and that's where we're saying our robot is. That's why we're printing the cells. And each of our motions has some noise, so that's why you see it's not 80 like it was before, because we have some chance that the robot didn't actually move. So you can see, and then you can see all of our visited cells. And you can see that this time these cells were visited because when we started off, the number of particles was heavier in one place only. So we assume that we have visited that cell already. So this one won't end in the same place as the other one did, and that's because of the distribution. So it really all depends on how the distribution is. In determining whether you visited a cell or not. So we're coming up to the end here. And once it hits the cell, it's going to see that it's visited all the cells, and then we end the program successfully. So that's all the code that we have. So once again, this is Zachary Chenoweth presenting Lab 3, Task 3, Particle Filters. And I hope you have a wonderful day.